So friends, in this episode of our chemical thermodynamics discussion, we are seeing entropy change associated in various processes. Let's first see isothermal reversible expansion. In isothermal expansion, change in temperature is zero. That means internal energy change is zero, or the internal energy of the system remains constant. So, if you give Q amount of heat to the system does equivalent amount of work, and therefore heat and work in isothermal reversible expansion is balanced each other but in opposite directions. So you can write for the expression for entropy change during this process, the heat can be replaced with work, and work in reversible isothermal expansion is this much, that is nRT log of final volume to initial volume, and therefore the change in entropy can be written in terms of the initial and final volumes during expansion. And as this Q amount of heat is given to the system by the surroundings involve a loss of heat Q, therefore an equivalent change in entropy occurs to the surroundings but in opposite direction. So the total entropy of the system is zero, and the process is not beneficial in terms of entropy, but the process occurs at the expense of energy, that is the process is energy driven. And let's now see the free expansion work. When the gas expands from high pressure region to the vacuum region, the work associated is zero and the heat associated is zero. This also we have seen in a previous lecture. Therefore, the entropy change of the system can be written as before, and the surroundings has no role in this process of expansion. Therefore, the entropy change associated with this process but experienced by the surroundings is zero. Therefore, the total entropy change during the process can be given like this, and this is always positive. So, during free expansion, the universe benefits in terms of entropy, that is, the process is entropy driven. Now let's see an adiabatic reversible expansion. As it is adiabatic process, the system has no communication with the surroundings. So when the system performs work, that is in the expense of internal energy, so the heat is zero during the process. Therefore, the change in entropy of the system during the process is zero. Likewise, the change in entropy of the surroundings is also zero because surroundings has no communication with the system during this process. So, surroundings has no role in that. The total entropy change during the process is hence zero. And now let's see some phase transition processes. Phase transition can be conversion from one phase to another at a given temperature, the characteristic transition temperature, like evaporation of liquid or sublimation of solid to vapor, whatever. And likewise, you can have phase transition from one crystalline form in the solid phase to another crystalline form. So this is also marks the phase transition. And during phase transition, when you write the entropy change associated in terms of heat, the heat at constant pressure, you can relate it as the enthalpy change of the transition. Therefore, here you can write the entropy change of phase transition in terms of the enthalpy of phase transition and the transition temperature, which is the characteristic temperature of the phase transition process. So, considering an exothermic process like a freezing or condensation process, as it is exothermic, the enthalpy change is negative. That means entropy change is negative. Therefore, the system entropy decreases during the process. But during this process, the heat liberated by the system is accepted by the surroundings. Therefore, surroundings has a huge gain in entropy, and in total, the universe entropy will be positive. That's why the process is favored. And for an endothermic process like boiling, you've got a positive enthalpy change, therefore a positive change in entropy. And let's now have a look on this table where you have got several liquids listed and their boiling points and enthalpy of vaporization. If you divide this enthalpy of vaporization with the temperature, you get the entropy of vaporization. And it is interesting to note that the entropy of vaporization for all the liquids lie in the same narrow range irrespective of their chemical nature. This empirical observation is concluded as Troughton's rule, that is, entropy of vaporization lie in the small range between 85 to 87 units. And now let's see the mixing process. Consider two gases A and B occupying volumes A and B are mixing into a total volume of VA plus VB. And what could be the entropy associated in this mixing process? So for mixing, each gas experience an expansion. So The entropy change associated in the expansion process. We have seen this before, and for each gas we can write that for the gas A, entropy change during this expansion can be given like this, where VA plus VB is the final volume, and for gas B you can write the same here. The total entropy change of mixing is the sum of the two entropies experienced by the gas A and gas B before you reach this expression, and for gases you can relate the volumes directly to the number of moles of the substance. So if you write it in terms of the number of moles of the substance and you rearrange this, you can write this entropy of mixing in terms of the mole fraction of A and the mole fraction of B. The chi A and chi B here represents the mole fraction of the two gases respectively. So the entropy change associated in a mixing process of two gases is given by this expression, which involves the expression of mole fraction of A and B. And that's all about the current discussion. And in the next discussion, we will see the third law of thermodynamics and the statistical entropy. Thank you.